This is lecture 22. In this lecture, we continue our discussion about associated primes. And eventually, all this is going to be used to clarify the idea of an irreducible decomposition, and in fact to refine it, and thereafter we will forget about irreducible decompositions and we'll know only that, only what we will learn. Okay, so here is a proposition about associated primes. Proposition. Let 0 to m1 to m2 to m3 to 0 be an exact sequence. Then associated primes of m2, associated primes of m1, the first module, is a subset of the associated primes of m2, and which is a subset of the union of the associated primes of m1 and the set of associated primes of m3. Okay. So the associated prime of the left one of any module is a subset of the associated primes of a larger module, and the associated primes of this middle module is a subset of the union of the associated primes of the submodule and the corresponding quotient. Okay. So this is what the proposition says. Proof. Okay. Let P be associated to M1. Then there exists an R-linear map there exists an R-linear map from R mod P to M1 This is, as we mentioned earlier in the previous lecture, although we said associated prime means an annihilator of a prime ideal that's an annihilator of an element, very often we just think of it in terms of such an injective map. Okay. Compose with the injective map M1 to M2 to see that. So both these are R-linear to get that P is associated to M2. Okay, so hence associated primes of M1 is inside associated primes of M2. Okay. So this is the first inclusion here. For the other, let's look at the other one. We have to work a little bit with element wise. So now let P be associated to M2. Okay, so therefore, there exists some x inside M2 such that its annihilator is P. Okay. Now, we consider the module, the submodule R times x, so all multiples of x intersect M1. So this is a submodule of Rx is a submodule of M. It is called a cyclic submodule because it has just one generator, okay, like a cyclic group. So it's called a cyclic submodule, okay, and that intersect M1. So now this is a submodule of M1. Okay, so let Y be inside here. Okay, write Y as R times X, and R has to be outside P because P kills X. Okay, so suppose Y is this. Okay. So I'm sorry, I didn't say R. Okay, let this be a non-zero. Okay, take Y non-zero. Okay, so R is not in P. So now we would like to understand what the annihilator of this y is. Let A in R be such that AY is 0. So we are looking for the annihilator of y. So this now implies that ARX is 0. This is happening inside M. This implies that AR is P, because that's the annihilator of X. But R is not in P, therefore A is in P. This is, we assume that Y is non-zero, and this is, so actually, sorry, I should not say let Y. Assume that this is non-zero. Okay, so sorry, I should have been more careful. Assume this is non-zero. It is not necessary that two submodules of M2, namely Rx and M1, need intersect at anything. The intersection need to contain a non-zero element. So first assume non-zero. That this is non-zero. Take a non-zero element. Then we go over this calculation, and then we are done. We conclude that A is in P. Okay. So in other words, so what does this calculation say? This says that annihilator in R of Y is P, and that just implies now that P is associated to M1. Okay. So let's just go over this proof. Just what does this half of the proof say? It says that if P is associated to M2 and X is an element whose annihilator is P, if this intersection is non-zero, then P is also associated to M1. That's what this argument says. Okay. Okay. So now assume that Rx intersect M1 is 0. Okay. So we have a surjective map from M1, M2 to M3, whose kernel is M1. Inside here is a submodule Rx. Now this composite map gives a map here, not necessarily surjective, but a map. Okay. What is this map? So let's, what is the nature of this map? Well, this thing, so this is R linear, this is R linear, so we get an R linear map from Rx to Rx to M3, and so okay, so this is a composite. This induces a map which is Rx. So remember, kernel of this map is M1. Kernel of this surjective map is M1. So Rx modulo Rx intersect M1 injects into M3. That's from this thing where we get this map. But this is 0, so this is isomorphic to Rx itself. That's because we are going modulo a 0 submodule. So in other words, Rx is a submodule of M3. So let me just quickly go over what we just said. Let's assume this. So we get a map from the natural surjective map from M2 to M3. Okay. That induces a map by first composing with this inclusion map from Rx. So we get a map like this, not necessarily surjective. We would like to prove that it is actually injective. What's the kernel of this map, of this diagonal map here? It is precisely this Rx intersect M1, but that is 0, so therefore the diagonal map is injective. Okay. So Rx, so now, but this is isomorphic to R mod P, so therefore, so therefore R mod P injects into M3. So to prove that this is isomorphic to R mod P, it just follows from the fact that if you take a map from R to M, 1 goes to X, the kernel is P, and therefore R mod P injects into M with 1 going to X, and if you have an injective map, then it is an isomorphism onto its image, not to the isomorphism to the larger module, but onto its image, but image is precisely this Rx. So this is an isomorphism. Okay, so therefore Rx is the R mod P injects into M3, so P is associated to M3. This is what we wanted to show. P is either associated to M1, that is if this set is non-zero, and if this set is 0, then it is associated to M3. Okay. So these are some basic properties, elementary property for associated primes. We will study more as we will restrict ourselves to Noetherian rings, but we will proceed as we go along. Okay. So next we need to generalize the idea of irreducible ideal. So remember we started with irreducible subsets of maximal spectrum or Z of I. Then we said, okay, let's do it for ideals, because if you want to do generality with all, in this algebraic setup, one needs to do it for ideals, but then it's actually much easier to do for modules, or okay, and we will do it so in that context. So first we need to extend the notion of irreducibility to modules. Okay, so definition. Okay, so again, R is a ring, commutative ring with say M an R module, N submodule of M. Say that N is an irreducible submodule of M if there does not exist N1, N2 such that, so what we would guess at this, by now at this point, such that N is not equal to N1, N is not equal to N, sorry, there does not exist, you remember, and N is their intersection. Okay. So if there does not exist such R modules, then say that, so these are, so if there does not exist N1 and 2 submodules of M, such that, okay, sorry about that, yeah. The point is all of this calculation, union, intersection is done inside some large module which is M. The same way we were working over ideals, where all of that, there was an ambient ring in which all the calculations were being done. Okay? So this is, we say it's an irreducible. Okay, so propositions. Let's assume R Noetherian, M finitely generated, N inside M submodule. Okay, then there exist irreducible submodules M1 through Mn of M such that N is their intersection. Okay, let's just so this is a proposition. If you have a Noetherian ring, a finitely generated module and a submodule, then the submodule can be, has an decomposition as an intersection of irreducible submodules. Okay. This is finitely many. So that's a thing. And proof I will skip because it is just repeating the argument for what we did for ideals. There's nothing new. Okay. So just if it is not true, then there will be an n1 which is strictly bigger than n, and so on. It will go on building a chain, but such an infinite ascending chain is not possible because we are inside a Noetherian module. Therefore, this is, it must admit such a decomposition. So proof is skipped. Okay, so this is analogous to the ideals. Okay, ideals case. There's nothing new here. So definition. Okay. So now we are going to begin putting extra structure or understand more what this irreducible decomposition will give us, is able to give us. Okay. So let n inside M be R modules, meaning submodule, not just a subset. Okay. Say that n is a primary submodule of M primary submodule of M if the associated primes of M mod n, this is a singleton set, is 1. Okay. It's a singleton set. That is, there's exactly one associated prime of M mod n. Say that n is a P primary submodule if the associated primes of M mod n is the singleton P. So here P is, let P be a prime ideal. Let P be a prime ideal of R. Say that n is a P primary submodule of M, if the associated primes of M mod n is, maybe let's just be precise here, M, if it's a singleton P. Okay. So this is just the previous definition with the extra information. What is that associated prime? Okay. So here is now the new thing about irreducible decomposition. Let proposition. Let R be Noetherian. N inside M, M finitely generated, N inside M irreducible, then N is a primary submodule of M. Okay. So irreducibility as such was some minimal structure. It was just some not equal to intersection of two ideals, each of which is bigger. There was not much extra structure to that. But now we are saying that that is not true in the case of interest, case of where most people are interested in, which is whether ring and modules are all Noetherian. Irreducibility does say that the module is primary. Okay. And we will try to understand what does this exactly mean. So what does primary mean? What extra structure that have? Just one more point, goes back to the definition. This is a statement not about M and N independently. It's a statement about the quotient. Okay, so just one remark, n is a primary submodule of M if and only if 0 is a primary submodule of M mod n, and similarly n is a p primary submodule of M if and only if 0 is a p-primary submodule of M mod n. The statement is always about M mod n and not about M and n separately. Okay? And we will see, so after this proposition we will see what it means to say that for a module 0 is primary or 0 is p primary. Okay? Okay, so let's prove this. So, by way of contradiction, assume that there is P and Q inside associated primes of M mod n, okay, and P different from Q. So, it is, in any case, M mod n has an associated, this set is non-empty. So, to say this is not primary is to say this is not primary, n is not primary inside M is to say that it has at least two elements, I call them P and Q. Okay. So, then R mod P injects into M mod n, okay, and let us say that the map is 1 bar goes to some x bar where x is inside M, but not in N. And similarly, R mod Q injects into M mod n, and in which 1 bar goes to some y bar and y is inside M. Okay. So, we have two such elements, x and y, with these properties. Okay. So, let Z be also an element of M, okay, such that Z bar is inside R x bar, which is a submodule of M mod n. So, this is okay. We would now argue that every element in the annihilator of Z bar is P. So, suppose A Z bar is 0. So, we are looking for annihilator of A inside. We are looking for an annihilator of A. Okay. So, what does that say? So, okay. Notice the following: R x bar is isomorphic to R mod P, because P is annihilator of this. Okay. And if Z bar inside here under this map maps to some R bar, okay, where R inside R but not in P is such that Rx is equal to R bar x bar is equal to Z bar. Such a thing exists because that's where we chose. Okay. So, we'll get a map like this. Okay. So, then A Z bar is equal to 0 if and only if. So, we're doing this calculation on this side, but the same thing as doing it over this side. A R bar is equal to 0 in R mod P. Okay. And that is the same thing as saying A R is inside P, okay, and which is because R is not inside P, the same thing as saying A is inside P. Okay. So, in other words, annihilator of every non-zero element of R x bar is P. Okay. Similarly, the annihilator of every non-zero element of R y bar, R y bar is Q. and these are distinct primes, so these cannot intersect. Okay, so this now implies that Rx bar intersect Ry bar is 0 inside M mod n, because it cannot contain a non-zero element, in which case that there will be a contradiction. Okay, so this is the okay. So this is these two are the intersection is 0 in M mod n. Okay. What does that say? It says that therefore in M, n is the intersection of n plus Rx intersect n plus Ry, okay, both of which are bigger than, so both of these are bigger than n, because we chose y and x to be non-zero, x bar and y bar to be non-zero elements, and that is a contradiction. Okay, and the contradiction came by assuming that associated primes of M mod n contains at least 2 elements. Okay, so that's it's non-empty, and we assume that it has at least 2 elements. Then we reached a contradiction, so it contains exactly 1. So therefore, n is primary. Okay, let's just summarize these results. Okay, corollary. I mean, we often write it in these. This is what was called the primary decomposition, which will are Noetherian, M finitely generated, and then for all n in n, there exist primary submodules, finitely many, M1 through Mn, such that n is the intersection of the MIs. N of them, yeah. Okay. So so this is called primary decomposition. We started from the idea of irreducible decomposition, proving using Noetherian hypothesis that every ideal or every submodule has a irreducible decomposition, prove that they are primary. So we still have not understood, explained what primary means, but that will come to. Okay, and so one more proposition, just to refine this a little bit. Let M1 and M2 inside M be P primary, for the same prime, that's the point, P primary submodules. Then M1 intersect M2 is P primary. Okay. So what does this mean? Okay. So we have so this is one of the usual statements, or an exact or a map that we use quite often in these when we discuss these things. So okay, so now we have a map from M. So we have maps from M to M mod Mi, M1, Mi, I from 1 and 2. Okay. So this gives a map from M to the direct sum. In this case, it's easy to visualize. Whatever x here goes to x mod M1, comma x mod M2. But this is, which we didn't discuss. Direct sum have certain category theory properties, and then it is from there it is automatic that there is such a map. Yeah. Okay. But what's the kernel? Kernel of this map is M1 intersect M2. Okay. So therefore we have M mod M1 intersect M2 sitting inside this direct sum. Which now means that associated primes of M mod M1 intersect M2 is a subset of the associated primes of M mod M1, direct sum M mod M2. Okay. And this is really associated primes of, for a direct sum, associated primes, one can just take unions. Okay, so this is related to the proposition that we saw immediately after about the short exact sequence, but a direct sum like this can be put into a short exact sequence which splits, and so it can be written in both different in this direction and as well as in the opposite direction, and from which we can conclude the statement. Okay, so this is true. But what is this? Both these are primary to the same P, so this is P. Okay, so M mod M1 intersect M2, so M1 intersect M2 is P primary. Okay. This is what we wanted to prove. So now we can strengthen the earlier corollary a little bit. R-Noetherian, M finitely generated, and N inside N, submodule. Then there exist primary submodules. Okay. Mi. Okay. I goes from 1 to N. Okay. Such that Mi is Pi primary Pi is different from Pj if I is different from j, and N is the intersection of these Mi's. Okay. In other words, in the earlier corollary where we saw this intersection, club all the ones with the same P together and call that thing just that thing Mi. Okay. So now we can just get this to be distinct. Okay. And so this is so we will stop here and we will continue discussing this further in the next lecture.